This will be the flow of the presentation. I'm going to introduce what is CFD and where we use it. Then what are the smokes fundamentals that are used in doing CFD, computational fluid dynamic analysis. Then few case studies, one related to a underground basement station, metro station, then a large atrium, an airport in this case, for a tunnel, and for a car park. And then I'll just briefly touch on the software used for CFD analysis. So, introduction to CFD. You see all flows for fluids, for gases and liquids both, are governed by mass conservation, energy conservation, and continuity equations. These together form equations which are partial differential equations, which are second degree partial differential equation known as Navier-Stokes equation. So the problem with these equations is they are quite complex, and analytical solutions to these equations is not possible. So we were not able to really evaluate or predict the behavior of air or liquid in past, but lately due to advances in computational power, availability of cheap computation, we can use that to do calculations using numerical methods and get solutions for the flow of a fluid, temperature changes, contaminant transportation, and all that. So that is what the whole domain of computational fluid dynamics is. So one CFD solution can yield results like velocity, pressure, density, temperature of fluids at different points in the space and time. The tasks that are involved in CFD, first of all, we have to prepare the model, which is pre-processing, which basically means creating a 3D model for the geometry and dividing that model into small geometries called meshes. Obviously, a 3D model for the CFD task is slightly different from a 3D model for, let's say, an architectural application. Then in a CFD model, we ignore a lot of unnecessary details that are required in the architecture detail. So we create those CFD model and then divide the whole domain into small volumes and solve the equations for those small volumes later. So this is called pre-processing. Then we set model equations, as in which equation will be solved where is the entrance, if there is an air conditioner or where there is a fan, how much is the air coming from that, if there are people standing, how much is the heat emitting from the people, and all those conditions are defined during setting the model. Then we solve the model equations and we get the solutions. This typically takes, like for this room, for this meeting room, if we solve a reasonable amount of time on a normal PC, would be about 12 hours. We will get a solutions on how the flow pattern is. Then the most important part is the verification and validation of those results. The results are as good as the input that you have given to achieve those results. So it's very important to validate and verify some common testing procedures, convergence checks, and normal physics principles are followed or not in the simulation results. Why CFD is a no-brainer? Because simulations as compared to experiments are much easier, cheaper, faster. You can have data on all the points that you want to. These are the typical applications of CFD. Over the years, it was traditionally more used in aerospace. Here you see chemical processing, hydraulic dams example, and HVAC, of course. Aerospace is where it all started. The first application of CFD were the aerofoil testing of aeroplanes, in which flow around an aerofoil was tested using experiments using CFD, and it was a big cost saving in terms of reducing testing. Then automotive, biomedical, power generation, even sports. A sportsman like Ian Thorpe uses CFD to improve his stroke so that he can move faster in water. And marine applications. So these are the various applications we have. Typical application we are discussing right now, the smoke simulation. The fundamental is that a fire of a certain size creates smoke and it creates heat. So both these can be simulated using CFD, how much smoke is being generated, how much heat is generated, and what path the smoke is taking and what path the heat is taking. The heat and the amount of smoke and heat generated will depend a lot upon what is burning. Like this paper will create less smoke and more heat as compared to a polythene, and also how much oxygen is available for burning. If there is less oxygen, then there will be more smoke. Intensity and the stage of fire. Stage of fire, typically every fire has a curve which has a flashover period in which it develops over a certain period of time. Then it reaches a fully developed stage and naturally it declines. So which stage of the fire we are depends on the fire intensity. These are the heat and smoke equations that are typically used. I think speaker before me explained in detail why we need to go in detail of fire safety design. CFD is another tool in that direction to save lives. Basically, as a ventilation engineer, what we focus while designing ventilation system is the control of smoke. We need to control the smoke so that most of the lives are harmed. Casualties occurs due to choking due to inhalation of smoke, and not many due to heat. So we need to ensure that the smoke movement is not in the escape paths, and also firefighters can come later and extinguish this fire. These are few assumptions that we make while doing CFD analysis. Like we assume smoke to be completely single phase, that is a gaseous phase, but actually there is some solid particles in the smoke which we ignore in the CFD model, which are actually not needed for doing ventilation studies. Then radiation due to fire is ignored because in a fire convection, in a ground fire, convection is much more faster than a radiation, so we can safely ignore that. And few more assumptions like that we take, but so we come to case studies. First of all is the design of underground metro train. This is actually a case study I'm presenting is for a retrofit job of an existing metro station in which there was no smoke ventilation design, there was only for normal ventilation. The NFPA 130 is the standard which is used for the smoke ventilation design for the metro rails and other rail systems as well. Apart from that, there are standards in EN 1050126 is a very good standard which is more followed in European areas. NFPA is more state. ASHRAE, Germany had a standard and which is known as RABT, Swiss standard, but all the standards talk about the same thing and they focus on give them more or less the same calculations. So here we have the